Thank you. I'm certainly pleased to be here today. And I think as you heard, my background then involves a bit more in the substance abuse realm, but it did start really with a study of rewards and basic reward systems. I have no disclosures. My work is supported by NIDA and by the Pennsylvania Department of Health, and I have no conflicts or professional relationships to disclose. So from Hershey, Pennsylvania. So addiction starts here. And this is a reasonable place for things to be. We have substrates that we in animals that are readily responsive to all manner of natural rewards. And the system this is a simplified version to a degree, but focusing primarily on the dopaminergic system. And it involves primarily a projection from the ventral tegmental area to the nucleus accumbens and to the prefrontal cortex and dorsal striatum. And there are, of course, many interactions with the amygdala, with the lateral hypothalamus, and important descending projections back to the nucleus accumbens from the prefrontal cortex. But dopamine has been a key player. And as I think was indicated in the talks earlier, it's a neurochemical that probably is involved in that final common pathway. How do we influence output, the final decision in terms of how we're going to behave? So this is just some evidence for the role of dopamine, looking at microdialysis data here in a female rat, and just showing that relative to the 100% baseline, that dopamine levels go up when the animal's exposed to the wheel, gets to run in the running wheel, when it's exposed to a new chamber, bedding, scented bedding, and then when it's given access to the male. It's elevated in response to consumption of chow for rats. It's elevated in consumption to sweets. Here the animals drank sucrose for 20 minutes. You've got a nice big increase in dopamine release. You get the same thing with saccharin. Dopamine is also sensitive to magnitude of reward. So here, Hajnal et al. Have shown increasing levels of dopamine in response to increasing concentrations of sweets. And Wolfram Schultz has shown similar data with measuring neural activity. These data are just showing response to romantic love. They used people who were wildly in love, and the VTA lit up when they saw the picture of that individual. Dopamine also is elevated in response to drugs. This is showing in response to cocaine, but they're also elevated in response to all drugs: cocaine, morphine, heroin, nicotine, caffeine, everything. And it's elevated in humans in response to drugs as well, which the imaging data allows us to see. So it starts here, and all is sort of well and good. But it ends here. Whether we're talking about addiction to food or sex or drugs or gambling, it does appear that there are many commonalities. And so we'll have to pay attention moving down the road. What are the commonalities and what are the differences between these addictions to different substrates, so to speak? So how does it happen? Well, currently I think everyone's agreeing, I'd say, that addiction is a brain disease that involves chronic relapse. Finally, putting that into motion, treatment-wise, for people addicted to food or drugs, I think is a much harder thing to do. But it is a disease of chronic relapse, and drug cues are a major precipitating factor. So with cocaine addiction, 50 to 90% of the people will relapse, and they'll relapse not just once, but repeatedly. So we need to we need to know how are these cues gaining this control over behavior, and when are these cues gaining control over behavior. So I'm going to address that a little bit. We know that all these natural rewards and drugs elicit the release of dopamine, and I think you've already heard a little bit about the cues. So the cues then can elicit the release of dopamine. And this was shown early on in Bart Hobel's laboratory, where animals had one taste cue, this conditioned cue, that had been paired with an intragastric infusion of polykos, and another cue that was paired with the intragastric infusion of water. Only the polykos paired cue then, when tested alone, would elicit the release of dopamine. So the cue does that. The same thing in Wolfram-Schultz data, but this alludes to something I think we've talked about, and that is that this is the neural response on the right to small, medium, and large volume of apple juice, fruit juice in a primate. And what we're seeing there is that the neural activity shown on the right isn't changing. This is in an experienced primate to the increasing volume of the sweet. But what's happening is it's changing to the cue that predicts the sweet. So the signal backs up, and the incentive, that whole incentive salience issue, the incentive is latched onto the cue. And it really made me wonder a little bit about this ICSS data you showed, the intracranial self-stimulation. You know, I've always thought of that as you're tapping into the reward pathway. Well, maybe you're actually tapping into the cue pathway, the seeking pathway. And so that's interesting. And so in humans, same thing. And you've seen some of this already, and it's more complex. These are very early data, but the cue elicits the response. And up here, what we're not seeing is activation of the accumbens there. This isn't an experienced user. The drug isn't even engaging that part of the accumbens at that point. So the cue then induces anticipation for the food or the drug, and it elicits the appropriate change in the accumbens. And so what I'm going to do here is kind of hone in a little bit on the role of the cue and looking at how animals change their response to the cue as a function of what's coming. So, and humans. So in this case, the animals are given 5 minutes access to a saccharin cue. 5 minutes later, they're injected with saline or morphine, and they're given 5 trials, 1 every other day, and then they get a test. So we want to know, okay, how are you going to respond for this sweet when you're anticipating drug? And what happens is, and this was shown first really in other ways with other drugs in 1969. So we're looking at saccharin intake here, milliliters in 5 minutes over trials. Everybody in the saline condition increases intake of the sweet over trials. But the other animals that have the saccharin morphine pairing, they're not going near the saccharin, not drinking it. Now, first of all, that's a little paradoxical. Why aren't animals responding for the cue that is predicting the drug? What's happening with dopamine? What we've seen so far is dopamine's elevated when it is associated with, in response to a cue that's associated with drug. So to study this, we had cannula in the nucleus accumbens, and we recorded dopamine following one saccharin, saline, or saccharin morphine pairing. Then the animals had a day off, then we had a test. And so we wanted to say, okay, are they going to avoid the taste that predicts morphine, like we saw before, and what's going to happen to dopamine? So the animals avoided the taste, the saccharin cue, when it was paired with morphine, compared to the controls. And what happened to dopamine is it pretty much followed suit. The animals in the saccharin saline condition, everybody increased their dopamine levels above baseline in their first exposure to the sweet. The saccharin saline animals showed a bigger increase then on their second exposure, which makes sense. The animals in the saccharin morphine condition, on the other hand, squelched. The dopamine system was not responding to that otherwise palatable taste cue when it was predicting drugs. So things are changing. Something's very different and different from what we would expect from an ordinary cue. And I think this has a little to do with the value of the saccharin cue, maybe being compared with the drug. But I think it has more to do with the process that goes into place when there's a cue that predicts a drug. And comes, say, out in front of the drug or out in front of the food. So we'll try and take a look at that a little bit more. So we found a number of things, I shouldn't put that there yet, a number of changes that occur in response to the taste cue when it predicts drug, when an animal's waiting for the drug. And what we started to think is that maybe what we're looking at is a conditioned anticipatory kind of a withdrawal. And so we trained animals where they had a taste paired with saline or a taste paired with morphine. And then after they were all trained, instead of injecting them with saline, we injected them with a low dose of naloxone. And what we wanted to see is, would the naloxone elicit a kind of a withdrawal? And we thought if they were anticipating drug, perhaps that would happen. So what happened here is this is intake of saccharin when paired with saline, and that's intake of saccharin on the CS plus trials when paired with morphine. So they avoided it. This is intake on the test day. They're drinking the CS minus, no problem with that flavored solution that says, hey, it's a saline day. They're not drinking the CS plus. We also yoked animals that got only a low amount because we're expecting a decrease in body weight out of these guys, and we don't want it to be just due to low intake here, so it's a little point. Sorry to bother you with it. Okay, so then we look at body weight. We give them this naloxone injection, look at body weight 2 hours later, and we found this huge decrease in body weight. It's the same animal because it's a within subject study. So they all have the same morphine history, but on this day, they got the taste cue that said, hey, drug's coming. And then instead of drug, they got this opiate blocker, which has no effect when they're not expecting drug. So the taste cue is eliciting anticipation of the drug. Now, perhaps craving, I'd be afraid to go there, but perhaps withdrawal, something we can consider a little more easily. So they're not responsive to the natural reward as occurs with drug, with these taste drug pairings with withdrawal. Corticosterone levels are elevated. I didn't show you that, but you actually have an increase in stress hormone levels, blunted dopamine levels, loss of body weight, and I'll talk about these other two briefly. So what I think's happening is that there's a process going on, a dynamic process, as an animal learns that a cue predicts a reward. And that has to do with preparedness, trying to get ready. What's coming? Food coming? Drug coming? And for humans and animals, when they're anticipating the drug, they can humans report, experiencing craving and withdrawal. These are human data from Sayet and Steve Wilson. And what this shows is that humans also exhibit a kind of aversiveness, negative affect when they're waiting to smoke. So what happens with these smokers is half are told, you're going to go in this session, and they're videotaping them. They're looking to see what kinds of behaviors they make and faces they make. You're not going to get to smoke after the session today. So they have no expectation to smoke. The others are told you're going to get to smoke at the end of the session. And then they just videotaped their behavior while they were waiting. And they found that those who were waiting to smoke, expecting to smoke, showed less positive affect and more negative affect. So waiting to smoke is an aversive kind of a situation, apparently. When they then put them in the fMRI, and this I like a lot because they were able to play for money. And they wanted to see how's the caudate, in this case, going to respond to winning and losing money. And they found that the caudate, for people who were instructed yes, meaning yes, you're going to get to smoke, but you have to wait, the activity in the caudate is just squelched. Whether they're responding to losing money or gaining money, the response is lower. So the caudate isn't responding to money in the same way that it would when someone thinks, hey, when I get out of here, I'm going to get to smoke. So I think a parallel thing is what's happening in the animals. They are in a kind of an aversive state. They're anticipating drug. They're devaluing a natural reward, and they're waiting. Now, these data I'd just like to give it to show you as well from Scott Bunce's lab. This is near-infrared imaging data, and he's looking at the activity of the frontal cortex to natural rewards, pictures of natural rewards, and to pictures of alcohol-related stimuli. So the people who are current alcoholics, they're responding to cues for alcohol, but they're not responding to puppies and babies and ice cream and other things. Over recovering alcoholics, those who are abstinent, want to be abstinent, their frontal cortex is responding less to the alcohol cues than the alcoholics, and starting to respond more to natural rewards. So the natural rewards are beginning to hit the radar as far as the frontal cortex is concerned. Now, how does this affect behavior? To know that, we need to like take a look at behavior, like for animals, self-administration behavior. So if they're in withdrawal, they're craving, you might think, okay, those animals that aren't responding to the natural reward might be more likely to take the drug. So in this case, they're given 5 minutes access to saccharin. 5 minutes later, they can lick on an empty spout operant. Every 10 licks gets them either saline or cocaine. They can take cocaine for an hour. They get one of these taste drug pairings every day for 13 trials in this case. So the first thing that we see is we're looking at intake of the taste cue. This is intake in the saccharin saline group. These two are the saccharin cocaine animals. So right away you see huge individual differences. These are outbred Sprague-Dawley rats. Some rats are really avoiding the taste cue, and some rats are consuming as though it's not paired with the opportunity to obtain cocaine. We find these individual differences all the time. If there's anything uniform, it's individual differences. And those individual differences in responsiveness to the cue predict drug taking. So the rats that really avoid the natural reward cue take 3 to 4 times as much drug. The animals that accept the natural reward take no more cocaine than other animals take of saline in this regimen. So we have big individual differences, and avoiding the cue predicts taking the drug. And Steve Wilson took a closer look at his human data. Excuse me. And he looked at the responsiveness of the ventral striatum, the accumbens, in humans. And he's looking at people who they were all told that they were going to get to smoke in this case. But when he looked at his data, and I had encouraged him to do it because I was, I saw a little, anytime I see variability, I'm thinking, yay, which doesn't work that way for most people. But so he looked at these individual differences, split them. And what he found is, for some people, their caudate actually wasn't responding when they were waiting to smoke. For others, their caudate was more responsive. So the red are the responsive folks to winning and losing money. The blue are those whose caudate's not responding to winning and losing money. And then he had seen my data with the self-administration, and so then he offered the people the opportunity to have a cigarette or to wait. And every 5 minutes they waited, they would earn more money. The people in red waited. They did not smoke. So those individuals, so we're looking at fMRI caudate activation. Those individuals whose caudate was responding to money, they waited, and they did not take the cigarette. The people shown in blue, they did not wait. They took the cigarette. They didn't go past the first 5-minute interval, as a matter of fact. So it's interesting. In the rats and the humans, whether one is or isn't responsive to natural rewards is a big thing. And that's probably true not just it's probably true, important for any addiction, that other rewards can hit the radar. So greater devaluation of natural rewards predicts greater responding for drug in animals and humans. And so wanted to know a little bit about when this thing develops. And are there, in the humans we saw some affective changes. Are there affective changes in the animal? And that's a hard question. In a way, not as hard maybe as craving, but is still an operational definition. What we know is that across phylogeny that animals and humans respond similarly to something that's placed in the mouth that's appetitive or sweet. Licking, lateral tongue movements, all of that. They respond similarly to something that's aversive. This one's got 20 years on the couch. Thank you, Mom. So they respond similarly to something that's aversive. They gape, and you can count the gapes, and that increases monotonically with increasing concentrations of, say, quinine. So I don't think this movie's going to run, to tell you the truth, because I'm not going to try it, because I didn't include my thing. But so you just score the number of licks and or the number of gapes. And so what we did is, and we'd done this previously, the animals were given one flavored solution, followed by 2 hours to take saline. The next day, they were given another flavored solution, followed by 2 hours to take cocaine. So they learned that grape flavored CS, grape-flavored saccharin, said saline, and the orange-flavored saccharin said it was going to be a cocaine day. And then what we wanted to know is what's going to happen. This was intraorally infused, so every minute they'd get an intraoral infusion of either orange or grape saccharin, and then they'd get whatever they were supposed to, the opportunity to take drug or saline for 2 hours. So we looked then at the orofacial responses of the animal to that taste cue. And I'll say that previously, so in 2008, with the Corelli lab, we published data showing that, in fact, the animals do gape. They show very aversive responses to the taste cue that predicts drug availability. But in that study, we did this at the end. At the end of training was when we assessed the taste reactivity behavior and when we correlated it then with drug taking. So what I wanted to know was what's happening, how quickly does this develop? And so what we found is that it develops immediately. So these are the high drug takers, these are gapes to the CS+. High drug takers do a lot of gaping, a lot of blah, 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 you know, when that stuff goes in their mouth. Low drug takers, almost none. This is the response to the CS-, and I have to apologize because the scales are different. So this is a little over 25. So the response to the low CS- is really pretty low. But the point is here, this is over the trials. They had 15 trials. The very second trial, one taste drug pairing, and these animals that are the bigger responders are gaping immediately to that taste cue. The CS+ in this study went before the CS-, and we see there's some generalization initially to the CS-, and then it dissipates. So immediately this process, I think a kind of a dynamic process between the cue, expecting the drug, and then changing the physiology, the neurochemistry in anticipation of the drug the next time happens immediately. And then if we correlate it with behavior, we find that the more gapes they make, these are the gapes on the third CS+ trial, the more gapes they make, the shorter their latency to take drug, the more load up they do. They go in there and they take cocaine quick. And the more aversive their face is overall, the more infusions they take. So this very early behavior is telling us what's coming down the road. Now we're looking at this with escalation. We're seeing it to predict escalation, and we're seeing it to predict other measures of addiction, like how hard will you work in the presence of a cue that says, hey, no drug, don't bother. Or how hard will you work when I actually put you on a progressive ratio schedule where I make it harder and harder and harder for you to get the drug. And this early behavior is telling us about those behaviors right now in our first studies. And I guess what I'm thinking is, I think that maybe a common view is that we need a lot of exposure to drug or alcohol to become addicted. And I don't know, I'm curious as to the possibility that it's starting very early, that we need to look early, and we need to intervene early. In human studies, there's a group who's been working with a very large population for a long time, and they're showing evidence for, these are individuals who just smoke one cigarette a week, and they have a lot of they meet a lot of the criteria for dependence already. And in some of their papers, they report that they are showing some of these signs even after having only had one puff. You know, somebody tries it, they didn't do it, but then they ask them questions about craving, about other things. And so it looks like these things come on really early. So by the time we're looking at adults, maybe we might, even with respect to obesity, maybe we need to be really paying a lot of attention early. So the last thing that I'll talk about are two risk factors. And one is sleep deprivation. And I often give talks to adolescents, and I ask them how many hours a day they sleep. And no one's probably surprised. I mean, most of them are sleeping less than 6 hours a night. And this is extraordinary and probably having a big impact. And we do know, of course, that sleep deprivation is now being linked to obesity. And it's a big issue. So we have a model where the animal's hooked up to EEGs and EMGs and then placed in this chamber, which is where he lives. And there's a little bar there. The bottom rotates so that when the animal starts to show non-REM sleep or REM sleep, if you want him to have a certain percentage of sleep deprivation, the bottom turns and then he runs into that little barrier and wakes him up. And so it's not a very nice thing to do to a rat, but it's the only way we can find out what's happening in this manner. There have been no animal models of chronic sleep restriction. So these animals in the chronic sleep restriction group are spending a lot more time in waking, large reduction in non-REM sleep, and reduction that's significant in REM sleep as well. It's about a 25% reduction, so we're talking about a 5 to 6 hour sleep night unless you are Marcy. I discovered she has quite a good sleeping habit. She's so glad I just made that public. Okay, so this is what we did. We started these animals on this. These are male Sprague-Dawley rats. And what we did is we deprived them, and then the next day they got to start to take cocaine for the first time ever. They had 3 days of fixed ratio, 1 progressive ratio trial. And so we're really just asking what happens with acquisition. If you're sleep deprived, is it going to change your acquisition? And what we found is, again, we have individual differences. We have low drug takers and high drug takers. We don't have a taste cue in this particular experiment. So these are the non-sleep restricted and sleep restricted animals. Being sleep deprived did not change responding. This is on a progressive ratio schedule. So we asked them, okay, how hard are you going to work for that cocaine? So they had 3 days exposure then by this point to the drug. And being sleep restricted did not change the behavior of the low drug takers. The high drug takers, on the other hand, it had a huge effect. And so they worked much harder than the high drug takers that were in the non-sleep restricted condition. So it's worrisome for me regarding adolescence. And I think that this model should be, focus on adolescents. I imagine they may be more vulnerable, or maybe they're not, we'd find out. But if they're not sleeping, that is when the kids are exposed to alcohol and drugs, and so it's a time that's key. These are human data showing that, so this was a total night sleep deprivation, and then what happened in this study is they looked at the activity in the anterior cingulate cortex to images of food. And they basically found that the sleep-deprived subjects were much more responsive to the images of food. So the deprivation, and then also these data and other data seem to be indicating that this is D2 receptor mediated. So for humans and animals with obesity and substance abuse, alcohol addiction, even nicotine, all of these things are associated with low D2 receptor expression, it appears. And so the deprivation is apparently changing the D2 receptor expression very quickly and modulating, maybe by that mechanism, maybe by some other, the response, increasing responsiveness to cues or to food-related stimuli. So the last one is the history of binging on fat. And so we'll have to hear a little bit more about restriction versus non-restriction. What happens in this model, Rebecca Corwin, we were interested in the comorbidity between eating disorders and substance abuse, which is about 30 or 40%. And so we were wanting to know if animals had a history of binging on fat, how would that modify their responsiveness for drug? So in Rebecca Corwin's model, rats are given chow. Everybody has free access to food all the time, so they shouldn't be hungry or need anything, so to speak. Then they're given a little vat of Crisco, and they get it 24 hours a day, or they get it 1 hour a day, 7 days a week, or they get it 1 hour a day, but just on Monday, Wednesday, and Friday. So that's sort of the restricted condition. So she did that for 8 weeks, and what happened to their behavior so then what she looks at is, okay, how much fat do you eat in an hour? And what she found is that, this is the chow, they are actually eating chow, not fat. The ad lib animals don't eat a lot in an hour. They have a lot of other hours to eat their fat. The daily animals significantly increase their intake of fat in an hour. The ad lib animals are just, going bananas. And they end up with this stuff on their whiskers and all over themselves. I mean, they are on a mission to eat that fat and eat it as fast as they can. So then she sent the animals to me. So they didn't get fat anymore, and they were just to eat fat any longer. And they were put in a paradigm where they could self-administer cocaine. And in that paradigm, we had every day there was a signal non-availability period. It's the Piazza model, where they could self-administer. Then they get a signal that says, hey, no drug now. Self-administer, no drug now. So it comes back to what Marcy was talking about. You're looking for persistent behavior. In the face of, in this case, cues that say, hey, there's no drug here. Don't bother. You're wasting your time. And then we also looked at a more progressive ratio where we said, hey, how hard are you going to work for this? You're going to go across this town and that town to go try and get this, drug or this food. So what we found is that this is the responding during signal non-availability. And what is evident is that the animals that were in the Monday, Wednesday, Friday condition, those animals that had restricted access to fat, they sought the drug twice as much as did the animals that were in the other condition. So something about having had the restricted access to the fat or having binged on the fat changed the way these animals are responding to drug. On progressive ratio, same thing. They worked much harder than the other animals did for drug. And finally, we do what Piazza does and give everybody a ranking. So you get a score of 1 point if you are in the top third of responders for signal non-availability, and the top third, another point if you're in the top third for responding on this willingness to work schedule. And so this is in the chow animals. We'll just sort of pay attention to the yellow part of this pie. For the chow animals, they, about 10-11% of them had a 2. So 10-11% were ahead of 2. Ad lib and daily, it was around 15-17%. And that's really typical of what's found in human population exposed to cocaine. Those are the percentage that presumably become addicted. And the rats when you're looking at a bunch of outbred animals. But this is what I think is the important part of the story. And that is that over half of the animals that had this history are exhibiting this addiction-like behavior for a drug. So something has changed in those animals, and I think it's probably important to figure that out. So I don't think that you. So dopamine tracks all these things: the natural rewards, the cues for the drugs. There are big individual differences in that. The cue seems to elicit an aversive state in anticipation of the drug. It does that very, very, very early. I think Weiss showed that an animal with one exposure to drug in a context will seek it 9 months later. That's just a rat. So this happens really early. And then responding for a drug is augmented by being sleep deprived or by history of binging on fat. Okay. Thank you.